Hi, everyone. Welcome to Chapter 10, Liquids, Solids, and Phase Changes. In Chapter 10, we're going to talk about what holds molecules together, what makes them a liquid, what makes them a solid, or a gas at room temperature. Now, we're not going to focus much on gases. We're going to focus mostly on the properties of liquids and solids in this chapter, as gases will have their own chapter. So that is fun. Now, this is a chapter that you're really going to want to pay attention to what we talk about here if you're planning on going into organic chemistry. Not that you shouldn't pay attention if you're not, but yes, this will come in handy and it will be important for questions that they like to ask, like which of the following has the highest boiling point or something like that. So let's get learning it, shall we? All right, these are your suggested chapter problems. If I were at home, these are what I would be doing, and you can always ask me questions at any point, as always. All right, so what does hold molecules together? In gases, actually, nothing really holds these particles together. They have complete freedom of motion, and when we talk about gases, we're going to talk about we make some assumptions using the kinetic molecular theory. So using the kinetic molecular theory of gases, one of the assumptions that we make is actually that gases feel no attraction to their neighbors. So feel little or no attraction for one another. And by doing that, we make some calculations that we are saying we're making this assumption that's an estimate, but it comes close to being the actual value at or around room temperature, standard temperature, and pressure. Now, in liquids, these particles are much closer together. So you see how much space we have here between the gas particles. We don't have nearly as much space between the particles here in the liquid. They still have some space, and if you were to knock a glass over, it would spill, and you would see that flow. That flow that you see is actually the molecules sliding past one another. Now, in gases, in solids, the particles are right up next to each other, and you can see there's very, very little space, if any, space in between the particles. So, although solids are moving, they are moving very little freedom of motion, and they're basically vibrating back and forth. So, a table, a chair, the particles are moving. They do have motion, and that is going to happen, but they can't move past one another. So, it's a very rigid state. So, gases have complete freedom of motion. They have the ability to move anywhere they want. If you were to open a container that contains a gas into a large room, it would eventually disperse throughout that room and fill up the entire room. So they have no definite shape or volume. Now, liquids, if I take a liquid and pour it from one container into another, I'll still have the same volume, but it will have a different shape. So liquids have a definite shape, a definite volume. I was thinking about how I want to write that, but no definite shape. Got to get used to writing while I'm talking or taking a pause, don't I? All right, now in solids, the particles are very ordered. They have both a definite shape and volume. No matter where I move that chair to, if I put it in one room or another, it is going to remain in that shape unless you do some type of, smash it or something like that. Now, liquids and solids are considered the condensed phases, where the atoms are more ordered. So gases are completely disordered, and solids are mostly ordered. For the most part, they're going to be very orderly. Liquids are kind of the least understood of all of our phases that we have. Well, the three main phases that we have. We're not going to talk about the fourth phase in this chapter, which would be a supercritical fluid, which are also very misunderstood. But liquids have properties in between that of complete disorder and order. So we have a little bit less understanding or they're more difficult to understand. This is liquid nitrogen. Fun to play with, but remember what we said in class, don't immerse any body parts or anything that you want to lose. So this is liquid nitrogen. And in the liquid, we see a lot of order. There's a little bit of space here, but not much order. Now, nitrogen is a nonpolar molecule, right? So it's going to have not a lot of traction to one another, and it's going to easily go into the gas phase. So this is the gas phase, lots of space in between these particles. So at room temperature, nitrogen would rather be a gas. So in this liquid state, it's really hard to keep it there. It has to be under pressure in order to keep it there. Once you release that pressure, it is going to turn into a gas. So it has to be at a very low temperature and under a high pressure in order to keep those molecules tight together like that. So one of the first things that we need to talk about, and we've talked about polarity of molecules, we've talked about polarity of our bonds in a molecule to figure out if a whole molecule is polar. But what we're going to look at here are these dipole moments. So looking at the bond here between hydrogen and fluorine, we know that we have electronegativity differences here. And we learned about electronegativity. It increases as you go up and to the right, and fluorine is the highest on the periodic table. So using the Pauling scale of electronegativity, which you're going to be given the values, you don't have to memorize them or anything. Hydrogen has a value of 2.1 and fluorine of 4.0. So in this case, this is more electronegative, meaning it's going to have more of the electron density. So we see that this is red, meaning it has more electron density, and the hydrogen has the blue, it's cold, it doesn't have as much of the electron density as fluorine does, because fluorine's the bully, it pulls the electrons towards itself. So we see this little funky looking symbol here, which is actually a Greek lowercase d for delta, and this is delta minus. So you remember way back when we had ionic compounds, and those had both positive and negative charges. So these are full charges, where there's an actual transfer of electrons. That's not what's happening here. So in here, let me change that color. Here, these are not full charges. It's an unequal sharing, but they're still sharing the electrons. So since they're still sharing, these are partial charges. So there's not a real transfer of electrons. It's just they're not being shared equally. So we have these partial charges here, and we need to be able to write those. Then what we do is we draw an arrow that says this end is the positive end, it's electropositive, and this end with the barbed end of the arrow is more electronegative. So it's going to get that barbed end of the arrow. This is called a dipole. So that is a dipole. So the dipole would point from hydrogen to fluorine, indicating that the electrons are being pulled toward fluorine or in the direction of fluorine. So if I asked you to draw a dipole for this molecule, you would draw what I have up here, but there's a lot of stuff up here. So I'm just going to erase this. You guys can always pause it and go back. I would say, okay, the bond between hydrogen and fluorine, this is my dipole, and label the partial positive and partial negative. This would be partial positive and this would be partial negative. So we put both of these together to show that dipole. Now, remember that when we do this, why did we talk about molecular geometry first? Why did we talk about that at all in overall molecular polarity? Because it's important in whether the molecule will be polar or not. Now, shape is important. So shape is important when talking about molecule polarity, because the shape of the molecule, if it was linear, might be polar, or excuse me, nonpolar, but if it was bent, it would be polar. So something like we talked about in class was water and how our life, the way our life is, our world is, our bodies are adapted to, is because water is polar. And if water wasn't polar, we would not have life as we know it. So bond dipoles can be thought of as vectors. And when they are going in the same direction, like something like this, we can assume they're the same value, they will cancel out. Also, if they're pointing directly away from each other, they will cancel out. Otherwise, they're going to add together. We could also do that on a diagonal. So if we go this way and this way, those also cancel. So let's take a look at these two molecules here. We have water. So this is water. Now, if water were linear, so like we said here, if hydrogen, oxygen, hydrogen. If this were linear, these would point at each other and they would cancel. But water is not polar, it's bent. And since it's bent, it has an extremely high boiling point for something of its size, an extremely high melting point, which allows us to have the life that we know with bodies that run with a lot of water involved and a lot of processes that involve water because of its properties. Now, carbon dioxide, which is written over here, so this is carbon dioxide, we can see that carbon here and oxygen, carbon is 2.5 and oxygen is 3.5. So this is a difference of 1 each. And they're going to have these that point away from each other and cancel out. So the dipole moment here is equal to 0. Now you don't need to know the value, you just need to know that it's not 0 in order to tell me that the molecule is polar. So let's look at the polarity here for each of these. Now CO2 we just looked at on the last screen. CCl4. I want you to pause this right now. Try to draw the molecular geometry of these. Do your best to draw it out. Again, I'm not going to grade your molecular geometry if your structure is written in the right shape. I'm not an artist. I don't expect you to be. But I want you to do your best because it will help you with determining the molecular polarity. So if you haven't already done so, pause this. Try to draw the molecular geometries for these two and figure out the individual dipole moments by taking the difference in the electronegativity, and we went over that scale. We went over the scale in class already, and if it is 0 to 0.4, it is nonpolar covalent. If it's 0.5 to 1.9, it is polar covalent, and if it's greater than or equal to 2, it's ionic. Now remember, this is just a general guideline, but that's what we're going to go with. We got to grade you somewhere. Got to figure out if you know it somewhere. So CO2 was actually just on the previous screen. Looks like this. The dipoles. This is 2.5, 3.5. Okay, so it's going to point this way and this way. They're exactly opposite, so they are going to cancel one another, and this would be nonpolar. All right, CCl4, C. Now this would be tetrahedral, so we have 2 in the plane. I know we didn't get to do this in lab. We had to do it on the internet, and that's not really that fortunate. But we have 2 that are in the plane and 2 that are not in the plane. And hopefully you were able to make some of these molecules at home and see that. So one is sticking out of the plane and one is sticking back away from the molecule. That's what we're trying to show you here. Now we put that there. So CCl4. Now the reason I like to show this molecule is because even though, let's take a look at this, chlorine has an electronegativity of 3.0 and carbon is 2.5. So these are polar bonds. The bonds are polar. They're going to point like this, and like this, and like this. Remember, this one's kind of coming out, and this one's kind of going back. But they are pointing all equidistant from one another. Remember, these are pointing to the 4 points. Let me write that in a different color. Of a tetrahedron. So they are going to be equally spaced. So even if you're struggling to see that, we know that all 4 of these are pointing equally spacing in opposite directions, which means there's not going to be any area of this molecule that's going to have more electron density than another. So anytime we see symmetry in a molecule, you can almost always, you can't think of an exception, say that it's nonpolar. So this would also be nonpolar. So these would cancel each other out. Now, erase this one and do pH3. So hopefully you've given this a try, at least. So P has a lone pair of electrons up here, taking up a lot of space. We're going to have one of these here, one with a wedge, and one with a dash. Now, if you didn't really get that exactly, this is what kind of pyramid? It's a triangle-based pyramid. So this is what we're seeing. This is trigonal pyramidal, or trigonal pyramidal, either way you look at it. Now, phosphorus has 2.1, and hydrogen is 2.1, 2.1, and 2.1. So none of these bonds are polar. These are all nonpolar. But I want you to look at this molecule, and I want you to tell me if you see an area of this molecule that might have more electron density than somewhere else. So while these electrons are not being pulled, there's no real dipole in this molecule, in the sense that the electrons are being pulled because these are all nonpolar. But there is an area of this molecule that has more electron density because it has a lone pair. Now, not every molecule that has a lone pair is going to be polar, but this one is. So one example would be something that has a central atom here, maybe something, X, X, and then it has, I'm just going to draw lines even though there's no little lines here just to show you the shape. Something like this where we have trigonal bipyramidal. So let me draw that in there for you if I can. Remember, I'm not an artist. Okay, so we have one pyramid coming this way, and then the other pyramid going this way, and we have trigonal bipyramidal. So this is giving us 2 pyramids, and these 3 are exactly 120 degrees apart. So even though there's 3 of them, and we would like to say, oh, 3 is an odd number, and there's 3 odd numbers of electrons, it doesn't matter because they're all equidistant apart from one another. So normally, this would be a linear molecule. All we see are these X's. And no matter what those X's are, they are 180 degrees apart. If they're the same, then it's going to be nonpolar. If one of them's polar and one of them's nonpolar, that's when you'll see polarity. But here, with those 3 lone pairs of electrons, they are not going to give us any polarity of this molecule at all because they're going to be equidistant from one another. So they're going to cancel each other out. Stuff can look like that, or symmetry. We look at this molecule, there's a lot of symmetry to it. So we're going to say that that one is nonpolar. So this would be nonpolar. So try to show you some of the ones that are a little bit more difficult. Hopefully that is it. We're going to have to practice this a lot, I know, and there's going to be some questions on it. But make sure you're trying it at home and asking questions. I'm here for you. Let's take a look at dichloroethene. This is a type of molecule that you might see as you go further in organic chemistry, or this is a very simple type of molecule like that we see. And it has 2 carbons, 2 hydrogens, and 2 chlorines. It exists as 3 different what we call isomers. There are different types of isomers out there. The ones that we're looking at here are structural isomers, well, we have geometric isomers mixed in here as well, but don't worry about that. Just saying that they are different ways to put these together. So these are on different carbons here and here. This one's below the double bond, this one's above the double bond, and these are both on the same carbon. So we see the cis. Cis means they're on the same side, meaning they're both above or both below the double bond. Trans means they're opposite. I can spell. On opposite sides of the double bond, because the double bond restricts the rotation, whereas something that has all single bonds is free to rotate. The double bond does not allow free rotation. That's all stuff that will help you when you go further in organic chemistry. But what we're going to look at right now is, are these molecules polar? So we can actually look at this in larger molecules and see what our dipoles do. So we're going to draw dipoles from carbon to chlorine, because carbon is 2.5, remember, and chlorine is 3.0. So that gives us an electronegativity difference of 0.5, which is polar. And we see one there, and we see one here, and they are going to add together to give us an overall dipole that looks something like this. So we don't really need to know what the number is. This number is going to end up being 1.9 when we look at this on the screen here. Okay, there we go. So this is the dipole moment, and it is polar because we do have an overall dipole, giving us a boiling point of 60.3 degrees. When we look here at the trans one, where they're opposite, we see that this dipole moment actually cancels out. So both of those are facing opposite directions. They're going to cancel each other out. This is going to be nonpolar, so the boiling point is going to be lower. So when we take a look at that boiling point, we're going to see that it's going to be lower. Now we look at the one where they're on the same carbon, and we see these two going in opposite directions. It's going to give us an overall dipole that looks something like this. And we're going to see a dipole moment of about 1.34. So that boiling point being about 31.7, having both those chlorines on the same carbon definitely changes the overall boiling point, making it much lower in this case. So how does boiling point change based on, how do the physical properties of a molecule change based on its overall polarity? That's what we're going to look at more and more in this chapter. So intermolecular forces. Intermolecular forces are what interacts, how the molecules interact with each other. So one thing that's really important to note here right away as we start are the bonds that we talked about, bonding forces, are called intramolecular forces, and they are responsible for the chemical properties. That's what we've been talking about. Now we're talking about intermolecular forces. And we say IMF a lot for short. So if you see me write IMF somewhere, that's what I'm talking about. So intermolecular forces are responsible for the physical properties. Boiling point, melting point, density. And they are all going to be determined by these three different types of intermolecular forces. We do have a fourth type of intermolecular force called ion dipole forces. We will talk about that, but this only happens when you have a polar molecule or a polar solvent, really, like water, for example, and an ionic compound that's going to be soluble. So a soluble ionic compound, something like that. So maybe we have like sodium chloride dissolved in water. We would have ions that are attracted to those dipoles in the water. So that would give us ion dipole forces. Then we have what are called van der Waals forces. That's a good term to remember. I'm not going to have you write them like that. We just do IMF for short normally. Dipole forces, London dispersion forces, and hydrogen bonds are what we're going to really focus on. And because these are going to determine the the difference between all the boiling points and all of that we're going to look at, because the ion dipoles are going to be a really special case if we do have them. Now, van der Waals forces are actually what we ignore when we talk about gases. So when we start talking about gases, you'll notice that term comes up once in a while as well. Sorry, I'm going to go back. One more thing to mention is these can both be attractive and they can be repulsive. So they can be mutual attraction or they can be mutual repulsion. So they can be repulsive and they can be attractive forces.